All right, thank you everybody, and welcome back from lunch. My name's Kevin Elzy. I'm a program analyst at the Advanced Simulation and Computing Office of the National Nuclear Security Administration, and I'll be moderating this session. And I would like to introduce Santiago Vargas from UCLA, who's studying theoretical and computational chemistry, and he did his practicum at the Lawrence Berkeley National Lab in 2022. And with that, his title is Ab Initio Enhancement of Machine Learning on Complex Chemistries. Welcome, Santiago.
Wait, which is? Again, thank you for the introduction. I'm going to be talking about, again, the ab initio enhancement of machine learning for complex chemistries. And there are three moving parts here. You have the ab initio part, which means I'm performing a quantum chemical calculation to inform my machine learning model. So this is at the descriptor side, not at the output side, which is, right, you generally need your labels from something, so that's normal. But like, we're using ab initio quantum mechanical calculations at the input, at our descriptor side. So we have machine learning models, which I won't talk too much about. And then finally, we're using them for complex chemistries. So one of the critiques I have of the field of cheminformatics and ChemML is that the data sets are too easy. So we're trying to move to more difficult data sets in the near future. So by way of introduction, let's take a day in the life of a computational chemist. So typically we are tasked with computing one of these properties. There are several more properties that you could compute, but generally it's something like, give me the optimized geometry of my structure, give me the orbital energy, so this gives us interactions. If you're worried about trying to build batteries, you might care about redox potentials. Excitation energies might be useful for solar cell design. And then bonding is just, foundational important information. So say you have a structure like this ruthenium complex. This is from one of our data sets. This is a really complicated structure. You're pretty far down the periodic table. It's a pretty big molecule. So running DFT on this is non-trivial. So what do you give your computer, right? How do you encode chemical information into your computer? So typically for a computational chemist, what you do is you're going to input positions and elements. How you get those positions can be any one of any method. It can be accurate, it can be not accurate. Just give your computer positions and elements, and you're going to pass that through some sort of workhorse algorithm. And for the most part, it's density functional theory. And then you're going to use that to evaluate forces and energies, which you can update your geometries with and then get a better geometry. And then finally, you might do something like calculate frequencies, which tells you that you're at a local minima. With that, you finally evaluate DFT one more time and get the thing that you were finally looking for. So this tells us nothing about the cost. This is a well-established, stable workflow. Most people will do this at some point if you are a computational chemist. But for this complex, this routine can take on the order of hours or days. So that's not useful for something that's like high throughput screening. And then kind of setting this up for machine learning, if you take this structure and change anything about it, add a carbon somewhere, remove a carbon in another place, change the metal, you're starting from scratch. You have to do this entire routine all over again, and there's really no learning from one structure to the other. So, right, this is a sales pitch for machine learning. Use machine learning for it, right? So the problem with that, and there are several, one is that you need a data set for machine learning. And typically for these tasks, you're using thousands of data points to millions of data points. So for something that takes an hour to days on a modern supercomputer, that's just not feasible to generate data sets of millions of data points. That's just too expensive for most folks. So we're going to move to simpler molecules, let's say water, for example, organics, and that's typically what the field will do. So you want the user experience to be the same as using DFT. So typically the inputs for machine learning models will be positions and elements, like it is for DFT, and you're going to get your labels of predicted property, whatever that may be. And then once you have a trained model, you simply cut out the DFT middleman, your oracle, and then in a reasonable chemical domain, you are able to make new predictions on similar structures, right? That's great. Instant evaluation, millisecond evaluation instead of hours or days. The problem with that is your model, it doesn't show the little cloud. Your model lives in a chemical space. It's only going to perform well in a space similar to where it was trained on. And if your data set only consists of organics, probably the most important ubiquitous data set in machine learning and chemistry, it's called QM9. QM9, the 9 means 9 heavy atoms, and those heavy atoms only consist of carbon, oxygen, nitrogen, and fluorine. So that's not particularly explorative across the periodic table or even chemical size, molecular size. So you can't really use this for a lot of interesting chemistry, and that's a huge downside. Data's still expensive to get, and what my work is trying to upend that and move towards more difficult chemistry. So F-block chemistry, if you're worried about nuclear nonproliferation, that might be of interest to you. If you're worried about energy, this is really important. You could not use organics for that for the most part. And my work is trying to work on difficult chemistries, larger swaths of chemical space, and return to these complex ruthenium transition metal complexes. And we're doing that with less data by introducing rich chemical information at input time, right? So instead of just giving it positions and elements, we're going to give it some complex chemical information. I'll talk about what that is in a second, but for now, we're doing more homework, but we're going to get a better model out of it with less data. So what that will look like in the long term is we're going to get DFT data that is machine learned. And you might think immediately like, okay, so I'm going to use DFT at my inputs to predict DFT at my outputs. That doesn't seem logical, right? But DFT has levels to it. And now we introduce that where DFT can take days, weeks for some approximations, or it can take almost seconds on other approximations. So what we want to do for the time being is use cheap DFT. That's going to give us descriptors. That's going to give us a model that will jump from cheap DFT to expensive DFT. And in a sentence, the advantage that should give us is that we're able to learn on difficult chemical domains and use less data while being more general in our model construction. So how we're going to do that, our rich chemical information is going to come in the form of what's called QTAME. QTAME is the quantum theory of atoms and molecules, and it is an atoms in molecules method. And what that means is you take your scalar field, which is electronic density, you do density functional theory, you get density out of it, and you're going to decompose it into chunks. And these chunks correspond to atomic basins, which are your atoms in your molecule. And what's nice about these chunks of 3D real space is that you can, to be very vague, you can do math on them. You can operate on them, you can perform convolutions, and you'll get descriptors. These descriptors have been mapped back to ideas such as bonding, covalency, aromaticity, stability, energetics, so forth. They're very chemical ideas, so it makes them very interpretable versus just positions and elements. What are you going to get out of that? You can't really interpret that. But if you have something that has been convolved into a concept, into a chemical concept, then you can maybe interpret your models and see how they actually work. And the other thing that's perhaps more important to me is that you get interaction graphs. And what this means is that you have your 3D chunks of real space, but you also have a measure of how they interact with one another. Do they even interact with each other at all, right? Because if you're next to each other in 3D space, that doesn't mean you interact with one another, right? So this takes a step back from the notion of covalent bonding and gives us just raw interactions. It doesn't care if it's ionic, hydrogen bonding, dative, metallic bonding. So what this means is that you can now operate on probably more complex, nuanced bonding, right? You're not covalent bonding anymore, you're just interacting. And this is useful for metals, for example. So to take a quick second to talk about where QTAME has been used in the past and sort of motivate it, we have a few studies from my group and one that isn't. So the first one is we correlated electric fields and their effects on QTAME values to enzyme activity. So a protein, KSI in this case, and trying to map its enzymatic activity. This was my first paper in grad school where we just used QTAME values to predict reaction barriers in Diels-Alder reactions. So proteins, small molecule reactions, and then here we have a study, I believe out of Portugal, where they analyzed bonding, so covalency, bonding strength, using QTAME, and this was on transition metal complexes. So this slide is to say that QTAME has been used all over the place. It is very general, and you don't need to reinvent the wheel if you want to do machine learning on proteins versus do machine learning on small molecules, which is really nice. So the last slide on QTAME is, and this starts getting into my work tangibly, is that in the past you'd have to do each one of these steps by hand, sort of handcraft all of these approaches using software. So you need to do DFT at scale to get your densities, then QTAME, parse that, format it, build graph neural networks around that, or any model around that. So I built high throughput code that interfaces with high performance compute so that you can do DFT, QTAME at scale, parse it, build models that natively work with these unique bond definitions. So you still have to burn a lot of CO2, but now you effectively have zero user intervention in that process. So this allows us to access giant data sets effectively. So I won't spare too much time on this, but we're using graph neural networks basically. Graph neural networks are neat and they've sort of been ubiquitous across machine learning in chemistry for probably like 5 or 6 years at this point. And yeah, they're very flexible. You can put any information. You can put QTAME, you can put more. They're nice. So getting to an example, a data set. We have more, but I do not have time to talk about it. This is a Libby data set. This was made by Christine Persson at Berkeley and Sam Blau, who is former CSGFer, where they computed 17,000 optimized battery electrolyte species. So this included magnesium and lithium, which means bonding is difficult. It includes a ton of non-covalent bonding, expanded octets, a whole slew of very nuanced bonding that is difficult if you're just using covalent bonding heuristics. So QTAME comes along, and we are able to make machine learning predictions on this. And what we're trying to predict are formation energies. So this is a really nice data set, but surprisingly enough, no machine learning benchmarks existed before this year. And we're trying to test not just raw performance, but can we create models that are more generalizable as a result of using QTame? And can we potentially create models that use less data? So just moving to raw performance. So here we have the MEV per atom. This is mean absolute error. And a model without QTame, annoyingly enough, actually does quite well. But we, we add QTame into the mix, and it does even better. But one of the things that we are interested in is also, can we make a model that uses less data? So in the very small data regime, so this is 100 data points, we have pretty awful errors for both a model with and without QTame. But as we add more and more data, the model with QTame opens up a bigger gap in performance versus the one without. So a 20% gap is non-trivial. Like, that's a much better model than one that doesn't have QTame. So that's learning, that is raw performance. And the last thing that we wanted to study, and I'll show here with the Libby data set, is generalizability. So I've mentioned it. A model, especially GNNs, are trained in a space, and they do not do well in a space outside of that. So, but you need to sort of codify what it means to have a chemical domain. This can mean a lot of different things. So you might train a data set on a certain molecular size, and then test on bigger molecules. Does your model do well there? Elements is really interesting to me, and QTame does well here, but I don't have time to talk about it. Can you train on one part of the periodic table and still make effective predictions on another part of the periodic table? And then what I'll talk about here today is charge. So what we wanted to do is train on a certain set of charges and then test on another set of charges. So what we did is we filtered the training set to only neutral species, the test set to only charged species, so +1 charge, -1 charge, retrained our models, did testing all over again, and what you should see is something like this. This is a model without QTame, where R-squared value of 0, sure, that's not a great metric, but R-squared value of 0, it's not quite a random number generator. You can see like a little bit of structure here, where you could sort of imagine, squint a little bit, just trying to shift these predictions down, and you can maybe get a reasonable model that predicts charged species here, which is well and good, but a model that has QTame in it is actually just able to natively make not groundbreaking predictions, but this model never saw a charged species. So just by adding ab initio information, you're actually able to get a somewhat serviceable model as a result, which is exciting because we've done other studies on molecular size, elemental generalization, and it showed decent results there too. So short talk, but we're talking about future work where we've worked on a bunch of other data sets, and I wanted to spare some time to sell something to you guys. We're working, this is my postdoc work, where we're collaborating with folks at Meta, I'll be at LBL, where if you are a fellow who has not done their practicum yet, you want to work on complex chemistries, you want to build general foundational machine learning models, talk to me, talk to Sam Blau. We'd be happy to have you guys. So that's a giant data set, probably the biggest data set of chemical information. We're also working on trying to generalize this to reaction properties, non-equilibrium chemistry, and then finally, as I mentioned before, a machine learning algorithm that can predict QTame values so you don't have to do DFT at all. And that's loosely based around this idea of link prediction, graph neural networks, and node prediction, graph neural networks. So with that, I'd love to thank the folks at CSGF, first of all, my collaborators at UCLA, my PI, Anna Sasia, the folks at Berkeley who I collaborated, did 2 practicums with Sam and Christine. It was a blast to work with them. So yeah, thanks to everyone, and any questions now?